In this video, we're going to look at the definition of what a ring homomorphism is. So we're going to start with the idea of letting R and S be two rings. They may be rings with identity, they may be rings without identity, they may be commutative, they may not be commutative. We don't know anything at all about these rings. We are going to start off with a function that is going to go from R to S, and we're going to call phi a ring homomorphism if phi has the following two properties. And these two properties are as follows. The first one says that for all elements inside the domain ring R, we have phi of A plus B is going to be phi of A plus phi of B. And the second property is going to say that for all elements A and B inside R, we have phi of A times B is equal to phi of A times phi of B. Now, if you think back to all of the functions that you've seen in all of the math classes that you've taken, these two properties are kind of new and they're kind of strange. The first one, this one here, sort of looks like one property that linear transformations have. And if you remember any of your group theory from your first abstract algebra class, this first one is an additive version of what the definition of a group homomorphism is. If you don't have to remember that, that's actually okay. What I want to do first of all, though, is actually look at in detail what these two properties are actually saying. So let's get a new board up. When we say that we have phi of A plus B equals phi of A plus phi of B. This is actually what we mean. The first thing is that this plus sign is saying first do the addition in ring R, and then we're going to apply phi to go from ring R to ring S. So this element is an element of S. So that guy is in S. On the other side of this equation, what we've got is these two things are saying first do phi. And that means that we're first going to go from ring R to ring S. So this element is now in S, and this element is now in S. And once we're in S, then we do the addition inside ring S. So the upshot of this equal sign, so what this upshot of this equal sign here is that it doesn't matter whether or not we add in R first and then do the ring homomorphism, or if we do the ring homomorphism first and then do the addition. What this equal sign here is saying is that those two processes are exactly equivalent to each other. The same kind of thing applies with the multiplication property of a ring homomorphism. So, when we write, let's get my handwriting to be just a little bit better. When we write phi of A times B equals phi of A times phi of B, we're actually doing exactly the same kind of thing. On the left-hand side, we are first multiplying inside ring R, and then we are applying the function phi to go from ring R to ring S. On the left-hand side of this equation, we are applying the function first. Let's get the right color here. I want to apply the function first. So we're going to go from ring R to ring S before we do any arithmetic. And then we're going to multiply inside ring S. So again, it's important to realize that this element is inside S, and these elements are inside S. And again, what this equal sign is saying is that it doesn't matter if we first do the multiplication inside ring R and then do the function, or if we apply the function first and then multiply inside ring S, that those two operations are exactly the same. And that's the definition of a ring homomorphism.